In this video, we're going to define and discuss both strong and weak acids and strong and weak bases. So let's start out with the definitions of these. Strong acids are molecular compounds that when they are put into water, they dissociate 100%. And when they dissociate, they form the hydronium ion. So for example, hydrochloric acid is a strong acid. If you put hydrochloric acid into water, the hydrochloric acid will dissociate 100%. So essentially, at equilibrium, all of your hydrochloric acid will be converted into the hydronium ion and the chloride ion. Strong bases, similar to that, they dissociate 100% in water, but instead of forming the hydronium ion, they form a hydroxide ion. So examples of that would be something like sodium hydroxide. If sodium hydroxide is put into water, it will completely dissociate, forming sodium ions and hydroxide ions. So there will be no sodium hydroxide remaining at equilibrium. All of it will be converted into sodium and hydroxide. Typically, strong bases are metal hydroxide, so ionic compounds that contain some cation that is a metal, and then the hydroxide anion. And of course, they have to be soluble. Not all hydroxide containing compounds are soluble. So if you have an ionic compound, a metal hydroxide, particularly with a group 1 or sometimes group 2 metal, those tend to be considered strong bases. So now let's define weak acids and weak bases. Weak acids are molecules that when put into water, they dissociate, but they do not dissociate completely. So they can dissociate less than 100%. And of course, when they dissociate, they must produce a hydronium ion in order to be considered an acid. So here we have acetic acid. When acetic acid is put into water, it dissociates, and you do form the hydronium ion and the acetate ion. However, not all of the acetic acid dissociates. So once equilibrium is reached, you still have some of the non or undissociated acetic acid remaining, and you have produced some hydronium and some acetate. So all of these species are present at equilibrium. Weak bases are molecules that accept a hydrogen ion in aqueous solution. An example of that would be something like ammonia is a good example. When ammonia is put into water, water will donate a proton and the ammonia will accept a proton. When ammonia accepts an H plus ion or proton, it forms the ammonium ion, and when water is deprotonated, it forms hydroxide. So hydroxide is also produced from weak bases, but that's generally produced by the dissociation of water. Now, of course, since it's weak, you still have some ammonia present. So not all of the ammonia is converted into ammonium. So at equilibrium, you still have some concentration of ammonia, some concentration of ammonium, and you've produced some hydroxides. So just to reiterate a little bit with weak and strong acids, a strong acid, let's say you put that into water and you start out with some concentration of HA. HA represents our strong acid. When put into water, it will dissociate completely. So you have no HA remaining, none of your acid remains. All of the acid has been converted into hydronium and its conjugate base A-. Weak acids, when put into water, here we have HA, we start out with some initial concentration of the weak acid, it partially dissociates. So you still have some concentration of your undissociated acid remaining, but you have produced some hydronium and some conjugate base A-. And then very weak acids are things that basically produced almost no hydronium or A minus, since there's almost zero dissociation. So let's look at this table, this chart here. Here we have a list of acids. Up top we have very strong acids. Down at the bottom we have weaker acids. And notice that if you have a strong acid that dissociates completely, it of course forms a conjugate base when it dissociates. The stronger the acid, the weaker of a base the conjugate base is. Weak acids, when they dissociate, they tend to form conjugate bases that are very strong conjugate bases. So they have a very strong tendency for accepting protons. Now, if you notice from that table, there are hundreds, if not thousands, of different acids. So how do you know if an acid is weak or strong just by looking at it? Well, there are some ways that we'll discuss, but in general, there are only a handful of strong acids. If you are familiar with the strong acids, then any other acid that you see that's not a strong acid must be a weak acid. So it's good to become familiar with the handful of strong acids and recognize those when you see them. So let's take a look at a problem. Here we have a strong acid, nitric acid, and it says what is the hydronium ion concentration in a 0.5 molar nitric acid solution. So pause the video, take a minute, and see if you can solve that. Okay. So one thing that we want to appreciate with strong acids is that they dissociate completely. Now, here I have written a chemical equation showing nitric acid plus water gives me the hydronium ion and its conjugate base, the nitrate ion. Now, since nitric acid is a strong acid, by definition it dissociates completely. So at equilibrium, or after dissociation, the concentration of nitric acid is 0. The concentration of hydronium is 0.5 molar, and the concentration of nitrate ion is 0.50 molar. So again, we understand that from the stoichiometry. For every 1 mole of nitric acid that dissociates, we produce 1 mole of hydronium and 1 mole of nitrate. So we get that ratio from our stoichiometry. So the answer, the concentration of hydronium would be 0.50 molar in this solution. Take a look at a second problem. What's the hydroxide ion concentration in a 0.130 molar potassium hydroxide solution? So pause the video and see if you can solve that. So here I have a chemical equation written. We have potassium hydroxide that dissociates in water to form potassium ion and hydroxide, and potassium hydroxide is a strong base. It's a metal hydroxide that's soluble, and it's a strong base, so it dissociates completely. Because of that, after dissociation, our potassium hydroxide concentration will be 0. For every 1 mole of potassium hydroxide that dissociates, we produce 1 mole of potassium, 1 mole of hydroxide. And so that's a 1-to-1-to-1 stoichiometry. So our concentration of hydroxide will be 0.130 molar at equilibrium. Okay. So be sure that you're familiar with strong acids and strong bases and be able to solve some problems involving those. Now, calculating the hydronium ion concentration produced by the dissociation of a weak acid or a weak base is more complicated than those with strong acids and strong bases because they do not dissociate 100%. Some dissociate 50%, some 1%, some much less than that. So we have to take into account the degree of dissociation when we're calculating the hydronium ion concentration produced by a weak acid or weak base. So we'll discuss that in another video, and of course you want to review that in your text.